Here we go. Continuing where we left off. I left off last time at voltage and electricity, and I want to spend a long time on that today because it confuses students and it confuses adults. And all you really understand about electricity right now is that if you plug something into the wall, it comes on and works. But there's a lot more to it. We're going to talk about Ohm's law. Ohm is one of these standard issue dead white guys. Yeah, here, I'll show you his picture in a second. There he is. Greg Ohm. No. Greg Ohm lived about 160 years ago and is famous. There. Standard issue famous white guy. He's dead. He worked with electricity and voltage. And this is what his specialty was in the 1830s and 40s, well, 20s, 30s, and 40s. Now, we take for granted some of the stuff that he did, but it's important that you know how it works. If we think about it in the water tank analogy, and that's why I'm using this side and a link to this side, because the water tank analogy is a lot easier than the other ways I used to show this. This is a lot better than the way I used to do it. But if you think of this as a water tank, the level of water is the potential voltage. How much power could I produce? Because that's voltage. It's a unit of power, energy. So how much voltage could I produce? If I have more water in the tank, I can produce more voltage. I have more power. And this pressure at the very end of the hose, right here at the bottom where the arrow is, represents the voltage. Now, don't take this literally. In reality, this is a whole bunch of electrons pushing in a wire from a battery or from another source. So the water is now the charge, more water, higher charge, more pressure here at the end. That's how we're storing our energy. Current is getting that out. And if I have a big pipe, if otherwise my levels are the same and my pipe is fairly large, I'll get a lot of energy out. If my pipe is fairly small, I won't get a lot of energy out. I'll get less. The amount that comes through is called amperage or ampere. 1 coulomb per second. It's a certain number of electrons per second past a certain point. And that's in amps or amperes, named after another dead white guy, Dr. Ampere. Standard issue dead white guys, I don't make the rules. That's just the ones who we name things after. I don't make this stuff up. I don't make the rules. Don't blame me. What's that? Still in chapter 0. Although this is part of chapter 1 too. I'm mixing and matching. So here at the same level of water, a bigger pipe will produce more amperage, more flow than a smaller pipe. You can get more water out of a fire hose than out of a garden hose or a straw. You with me? That makes sense. That's all we're talking about. Except we're talking about it in electrons and electricity. Excuse me. If I want the same amount of flow, the same number of electrons per second, in a smaller pipe, I have to have a lot more electrons to start with. And notice how much higher the water level is. I have a lot more to start with here, because I need more in order to be pushing hard enough to get just the same amount at the bottom. I have a bigger pipe, I need fewer. I don't need as much total charge before. I don't need as high a water level at first to get equal amounts coming out. So if I have a smaller pipe, I have to push harder. That's what we're talking about. That's all it means. Excuse me. So the water, the level of water, is the charge, how much I've got. The pressure is how hard it's pushing down. More charge will have greater pressure. That's your voltage. Flow is how much is actually going through. It's the current measured in amps, and how big your hose is, or other conveyance, your wire in the case of electricity, that will give you resistance. So just here, looking at this, the same level of water will give you more amperage, more stuff flowing through a bigger pipe than a smaller pipe. Yes? I told you, this is a lot better example than the one I gave. So those with me last year will attest to that. Resistance is how easy it is to get those electrons through. In this example, and this is in ohms, you got a straight path. There's little resistance. It's going to flow. You put some resistance in there. In this case, it's squeezed a little. It's going to be harder to push it through. It's going to take more energy to push through that resistance, that crimp that we see right here. It's going to take more energy to push through this and get the same amount at the end. This is how valves work in your pipes at home. This is how electricity works in a switch or in a light bulb or in a computer. Ohm said that voltage and current and resistance are all related. V for voltage, I for current, measured in amps, R for resistance. And here's a picture of that. And remember, this is oversimplified enough that you can actually understand it in terms of water, and we're really working with it in terms of electrons, but it works the same way. Notice that while we have 1 volt starting, because that's the level of the water, because the pipe is so much smaller, our amperage is smaller. And the pipe smaller is why it's 2 ohms of resistance instead of 1. Excuse me. Say again? No? All right. Ask? No? All right. Let me move on to this one. This is where I stopped the lecture last time. But let's talk about what this means in terms of power you deal with every day. Voltage is a measure of force, pushing electrons through a circuit. In the United States, our ground power, the electrical outlets you have at home and we have here, are 110 volts AC, so alternating current, as opposed to DC, which is direct current. That part isn't as important as the fact it's measured in volts, 110 volts. That is a measure of how much energy is being pushed at any given point through the circuits at your house. It's available to push through your appliances because it's sitting at your electrical outlets or light switches. It actually can be measured even at rest. It's kind of bizarre. It's how some of these electrical finders, you can wave it at the wall and it'll show you all your wires themselves. It's measured in volts AC. We have 110 volts is considered standard. Now the electric company gets away with a lot because they say it's 110. But it could be up to 115 volts and not be a problem. 115 volts, the lights will shine a little brighter. And your air conditioner will cool a little faster. And your refrigerator will run a little less long. Most people don't even notice it. Some people do. Maybe you're one of those. But gee, the lights look a little brighter today. You may be up to 115 volts. The electric company calls that 110 because they make the rules. And that was a really good question. Why? Because they're in charge. And it just is. Now, they could drop it all the way to 108 volts. And especially in the summer, we see that. 108 volts, the electric company says, is still 110. Below 108, your lights start to dim a little. It's what we call a brownout. And you've probably experienced this where you're looking, gee, those lights just aren't as bright as usual. Say again? Okay. You need to be taking notes from this. And you need to be listening to everything I say. So at below 108 volts, your air conditioner motor is struggling to move. And it works a lot harder to cool your house. The refrigerator motor will work a lot harder and very often won't even work at all. Below about 105, most of them automatically shut off because they don't want to damage themselves. But they're having to work really hard because they're just not getting enough power. Instead of getting 110, they're getting 108. That's making it a little slower. And below that, below 108, we have a sag. We have a brownout condition. The lights turn brown. You can really see this in the old incandescents, but I can even see it in the fluorescents, that they get a little dimmer. When we have a brownout here, my projector actually gets dimmer. You can tell. Later. The next step below brownout is blackout, when they shut off the power entirely. We try and avoid those. But it's very common for us to have brownouts. We had one yesterday, or no, Monday, when we had the 102 degrees or 101 degrees, whatever it was. If you listened to the air conditioners work, they're working harder. And only part of that is that it's so hot and they're having trouble dissipating the heat while they take it out of your house to give you nice cool air. Part of it is that they weren't getting enough power to run because the voltage was low. The power company does what they can to provide you with 110 volts. They do their best. It's hard when things get really hot. Part of it is that everybody's using their air conditioner. Part of it is that heat makes it harder to push electricity through wires, which is counterintuitive because you've been taught that heat is good because it makes the electrons move faster. You took science. Electrons move faster, so it'll be easier to make through the wires. Up to a certain point, that's true. Above about 98 or 99 degrees Fahrenheit, about 61, that's wrong, about 52 degrees centigrade, it's harder. It's just weird how electricity flowing through copper works, or steel, depending on what your wires are made of. We'll come to that in a minute. But there's your voltage. I can go to my wall. I should always see 110 volts. How often will I see exactly 110 volts? Yeah, it approaches 0, but it'll average to that. If I don't have enough voltage, my motors might burn out. Good example is the clocks. It is not 10:15. It's 12:15. It's catching up. Yes, yesterday it was right. Today it's off. Maybe it'll be right tomorrow, maybe not. These clocks are rated at 100 years. I've worked with clocks just like this that are 100 years old and running just the same as the day they were built. And yet ours are burning out. The motors are burning out because the voltage they are getting is too low. They are physically not having enough voltage to keep them running, and that's why they're not working right. It's a design flaw of the school. Design plus construction flaws. The wires are actually too small. Should have used higher gauge wire. But what's important is that those are burning out because they're not getting enough voltage. They're not getting enough power to make them work. If they were getting the proper line voltage, these clocks would never be wrong and would never wear out. I say that, and I'm actually quite serious. I worked at a school once that when I was there was 70 years old. And my clock blew up one day because we had a power surge. It just stopped working. So I called my maintenance guy, my head custodian called the district. The clock guy came out because that's all he did was clocks. This was in Sacramento, and we were a large district. We had 115 sites. That's plenty of work for a clock guy to do only clocks. And he popped in another clock, and I said, well, where'd you get that? Well, such and such an office, they're using it as an office. It was built as a school over 100 years before. They're not going to miss this clock. So he popped it in my classroom. It was over 100 years old. Worked like a champ. It was just like the one I have actually. It looked the same, except it had a brown edge around where I have the gray. That was the only difference. It looked identical. The innards were identical. It still worked. And the clock guy said, yeah, I see what's wrong. It's got a loose wire in here. He was going to take it back to his shop and fix it and toss it in another classroom. They're easily repaired when they get proper line voltage. If they don't get proper line voltage, they wear out because the motors burn out because they're working so hard. So that's voltage. Current, which is measured in amps, is how much I can put through at a given time. How much electricity can I put through a circuit at a time? And that's measured for several reasons. Measured, a lot of it has to do with what equipment I am going to attach to it. A lot of it has to do with what size wires do I have in the wall. You at home have probably 200 amp service. Most homes do. Sometimes you'll only have 100 amps if your house is over about 50 years old. But the vast majority of you will have 200 amps of service. That means that at any given time you could draw 200 amps of power maximum. It's hard to get to that much power because even an air conditioner will only run about 15 or 20 amps. And you have 200 to play with. It's a pretty good sized number. Would you trip it? Yes, I've known people to trip their main. I've never tripped my main. I've never drawn that much power. And that's me drawing a lot of power for the equipment that I have. You're not going to worry about it at home, usually. Well, each of your individual circuits also has a circuit breaker or fuse, and it has its own. So you might have 200 amps of service. You might have 200 amps of service, but then you split that down into each individual circuit in your house. Yes? Yeah, you might trip an individual room, but it's not at 200 amps of service. It's probably at 15 amps. And 2 hair dryers plus a curling iron is about 19 amps. Santa? Let's not ask questions. They're probably fixing the air conditioner. I don't have rats in this building. I have them in the other room. Okay, so moving on. Current in amps. Each of your circuit breakers is either 15 or 20 amps usually. At your house, most of them will be 15 amps. And you'll have 15 amps of service for most things that you do. Sometimes you'll have multiple 15 amp circuits, but as a general rule, you'll have one 15 amp circuit, and that'll service lights and plugs in a room. It's okay. Santa's a good guy. No, he's not. Okay, he does breaking and entering on on a huge basis, but he only does it once a year, and that's not today. Yeah, that's true. He's a stalker. I agree. Yes? Let's move on. So, current. In here, I have, in my conduit, I have 20 amp circuits. And I just told you at home you generally have 15. Why would I want 20 amp circuits?
Because you need more amp circuits.
Yeah, I need more in here. How come I need more? Yeah, because I've got a ton of computers. Here.
I deserve a gold star.
I'll have to get you one. I don't have one in the drawer. Yeah, I have a lot of computers. If you notice, things are plugged in a certain way. That's not an accident. Back when I opened the lab, I had some giant computers one year. The towers were this tall from the table. I mean, they were huge. These things were enormous towers. And the monitors I had filled 2/3 of the desk because they were the old CRTs. They were 17-inch, beautiful monitors. They drew so much power. The monitors generated so much heat that for 2 years running, energy management checked my heater, my furnace, because I didn't run any natural gas. I didn't burn any. And yet the room was sitting at 80 degrees or 85. Or one day after a holiday, after a long weekend, it was 95 in here and it was 40 degrees outside. Because the monitors themselves were generating heat, the computers were generating heat. They drew so much power that I actually came in early and I would turn them on in sequence, in a certain sequence, so I wouldn't blow the circuit, because it's when you first turn it on that it draws the most power. And so I drew a lot of power. I drew 1/3 of the power for the school. Now I just draw more power than the rest of the building combined. But I left the windows open in the winter to vent the heat. I would open the door on a Monday morning especially, and it would just billow out this cloud of heat hitting the cold air. Steam, yes. Actually more fog, but same idea. Massive amounts of heat. That's why I have so much electricity in here, is because I need to have that much electricity. Now, it's not near as bad now, because even with all of your computers, these monitors draw 7 or 8 watts instead of 75 watts or 115 watts. I had one. I mean, they draw so much lower now that I don't worry about it as much, and I can have you. And the Wise Thin clients draw 1/3 of a watt each at maximum. Most of the time, they're sitting at about 1/3 of that. But current is a measure of how much I can push through. It's generally determined. It's generally determined by how big the wires are. Bigger wires can handle more power. If you have a 15 amp circuit, you need to not put a 20 amp breaker, because the wires will burn up before the circuit trips, and then you'll have a fire. Fires are bad.
That's a lot to write.
Fires are bad would be something to write.
Oh, no, I know that.
Yeah, okay.
I'm not talking about
Oh, the other stuff? All right. So current is in amps. That's what your circuit breakers, or if you're in an older house, you might have a fuse box. Generally, you have to have a house built before 1946 or so to have fuses still. And most people there have updated them. Similar to the fuses in your car. Someone asked me that last period. Yeah. Okay. Power is voltage times current, and we refer to that as watts. So you have voltage and you have amperes. You multiply them together, that's how much power you can push. If I want the same amount of power, I can adjust my voltage and my amperes and they'll move, one will get bigger and one will get smaller because we're multiplying them together. Voltage times current, V times A. If you look at the high power lines that snake from city to city, we've got some east of town, you know what I'm talking about, those giant things. Yeah, the giant metal ones. They are high voltage lines. Where we have 110 volts, they'll carry 100,000 volts. But if I'm at 20 amps, they're at 1/1,000,000th of an amp, roughly. Because it's a direct correlation. The number, the watts, the power has to stay the same. If I increase my wattage, I lower my, if I increase my voltage, I lower my amperage. Is that, you see it now? This equals that times that. Because that's the rule. That's how we measure it. This times that equals this. Voltage times current equals power. If I want power to stay the same, and I change my voltage, I have to change my current the other direction. If I make my voltage higher, I make my current lower. Because they still have to multiply to get to the same place. I don't know. I don't remember. Resistance then is opposition to flow. Stuff like a piece of metal will have very little resistance. It's easy to put electricity through them, easy to push electrons through them. But your desktop is made of wood. It's hard to push electrons through them. It's hard to push electrons through the wood. Can it be done? Yes. Give an example of where you might see electrons flow through wood. Somebody said something related. Lightning. You said thunder. You said thunder. So, lightning. Incredibly high power, lots of current at a high voltage will go right through wood. If you're in the way, it'll go right through you and we'll scoop you up with a shovel. Because really, that's the easiest way. Well, might use a broom. A vacuum, yeah, maybe. We'll have to have a really good filter. You can't. I didn't say you couldn't survive it. I'm saying that we'll deal with your remains because the odds are against you. Yeah. There's a lot of things that'll happen to you if you're struck by lightning. But that's what we're talking about, resistance. If I give enough power, nothing, it's irresistible. It'll go through. If I have high enough power, which is your third one, your watts, if my wattage is high enough, my total is big enough, I can push through anything. And, lightning tends to have really low current, but incredibly high voltage. It's plenty enough to kill you, yes. We got to be careful of it. And resistance then is measured in ohms. Lower resistance is good. Lower resistance will let our circuit flow, will let information flow through it. That was weird. Lower resistance will let electricity flow through my circuit so that I can... Is it ever going to work? So, yes. So, there's that. Any questions on electricity? Question? Can't hear him. Yes, there is a measure of voltage above which you're dead. I don't know it off the top of my head. I don't need that information on a regular basis. It's something you probably should know, but you're going to be dead anyway and you won't really care. All right, last thing before I let you close up shop, because you've got about 30 seconds. Back to school night is tonight. Please send your parents. I want to meet them all. Yes, give them your schedule so they can come. Please stack the chairs, yes.